Skylar, you got a problem? Matt, you got a problem?
Yeah.
What's your problem?
There's no standard deviation.
There's no what?
It doesn't tell you the standard deviation.
Of what?
Of the population.
Yes. Take a close look at this problem. Can you do this problem? No. And this is real world. Think about this. I guess they can make up like phony diamonds from nothing. Okay? You're going to take a sample. If you don't know the mean amount of carats this thing can produce, are you ever going to know the standard deviation for every particular diamond they can make up? Never! You're never going to know that. All the problems we've been doing up to this point are worthless. It's not real world. You're not going to be able to do it. This is what's going to happen. You're going to go take a sample and then you're going to be stuck. So what are you going to do? Come on. We've actually talked about it before. What are you going to do? Any suggestions? Yeah.
I would guess you have to put your best guess at the mean.
No, not the mean. What are we missing again? No, I'm not going to just guess.
So I'm guessing there's a connection between how it's a normal distribution and that will somehow correlate with the standard deviation.
Well,
I'm going to scratch my head out.
Okay.
Yeah.
Didn't we learn something where it was like 2 standard deviations? Or,
yeah, it's
it's
empirical,
like
that's normal distribution stuff. Yeah.
When we find, well, say the X bar of that, and then find each error from the X bar.
Okay, so what do you calculate? What are you doing?
Finding the average error from the X bar.
And what's that called?
The standard deviation.
Of the
X bar, or the sample.
of the sample. Doesn't this little sample have a standard deviation? Now, is the standard deviation from this little sample going to be the standard deviation from the entire population?
No.
But is it at least a guess? Is it at least a place to start? And that's what we're going to do. We're going to use this guy as a guess for what this value is. Now understand, we know it's not necessarily going to be that accurate, but we'll take care of that in a second. It's called the t-distribution. Okay. All right, go ahead and copy down the notes and then we'll... All right, they're going to try to mess with you in May. They're going to try to give you all kinds of weird reasons why you use this crazy t-distribution. There is only one reason. It's when we do not know the population standard deviation. They're going to kind of confuse you with sample size. All of a sudden, no. When we are not given or we do not know the population standard deviation, that is the reason why we go to the t-distribution. And that is every problem in the real world. Okay? We're never going to know the population standard deviation if we don't even know the mean. Okay, so we're going to go to this t-distribution. Okay, so we're going to use this sample standard deviation. We're going to use the standard deviation we got from our little sample to try to replace or to predict what the population standard deviation would be. Okay, now, due to the fact that we're using the sample to try to predict for the overall population distribution standard deviation, there's a great deal of uncertainty in that. I mean, we know we don't have the right answer. We may not really even be that close. Okay? So the t-distribution looks a little bit different than the z-distribution, which is the one we've been using so far. It is a little more spread out. Those x-bars are a little bit further out due to that uncertainty. So in this problem, what we'd have to go out like 1.645 standard deviations to capture 90% of the x-bars. Now the x-bars are more spread out. We're going to have to go more than 1.645 standard deviations. Our confidence intervals are going to get wider because of that uncertainty. Okay? All right, now, here's the thing about this, though. There's another factor that's taken into consideration here. Our sample size here was 6. So we're going to get a standard deviation from this little sample size of 6. Probably don't think it's, it's an estimate, but don't really think necessarily it'll be that close. But what if my sample size was like 100? Would I have a little more confidence in the sample standard deviation I got from this for predicting it all because my sample size was bigger? You bet. So the t-distribution actually moves around a little bit. This red line, the t-distribution, as you go to a larger sample size, will actually start getting closer and closer to the original z-distribution. So as you get a larger sample size, you have more confidence in your sample standard deviation that's estimating your population standard deviation, so the t distribution looks more and more like your z distribution. We call this degrees of freedom. You've seen this word before, okay? It's just a measure of how big the sample was. Now, why do they call it degrees of freedom? I don't really understand this that much, but here's the idea behind it. Let's say I have 6 numbers, and I know what the mean is. If 5 of them can be whatever they want, but if I know what these 5 are, could I figure out what the last number has to be? So in other words, these 5 are free to be whatever they want to be. The last one's no longer free. So that's why we've got this formula for the degrees of freedom of n minus 1. 5 of these are free to be whatever they want. And that's what we're going to use as to help us figure out how much we should trust this particular estimate. Okay? Okay, let's do it. See what changes. Okay, let's do this confidence interval and see what changes here. Now, obviously, our formulas are going to change a little bit. Okay, now here's the deal. Normally, we'd write z here with the population standard deviation. Since we don't know the population standard deviation, we're going to use the sample standard deviation. These two always go with each other. Okay, because we're using the sample standard deviation, we're going to be using the t-crit value. Okay. Also, there's one other formula that's used in your book. We've talked about this before, but they give it a special name. Remember we had all those X bars on our back wall? To figure out how spread out they were, we have that formula, sigma over square root of n. Okay? It's basically the standard deviation of all the X bars. Okay, they give it a fancy name. They're going to call it the standard error of the mean. Okay? It's just the standard deviation of of your sampling distribution. Okay? Sometimes you see SEM, so don't freak out. That's just what the standard error of the mean is. All right, let's do the confidence interval. What's the first thing that we do when we do a confidence interval? Good review for tomorrow. Population parameter. Anybody think anything would change there because we're doing this different distribution? No, it's the same. We're just defining what the variable is we're looking at. All right, let's take a look at the assumptions. Anything going to change in our first assumption about trying to figure out if we took a good sample or not? No. All right, number 2. Anything going to change in this one? Okay, the answer is no. All right, here's the deal. This is your first confusing thing here. Why are we doing this assumption? We're just trying to see if that formula is the right formula. And the right formula is the standard deviation in there. That's the correct formula. Okay, so you're not plugging in any S's here. Remember, this is just trying to see, hey, is this right? Or is it some different formula I have to use? Okay, so you still write it like that. Nothing changes there. Okay, we're just checking out if our sample size wasn't too big, that's the formula. All right, how about assumption 3, normal sampling distribution? Is anything going to change here? No, it's the same deal. Everything's the same. I talked just briefly yesterday about, remember I said the sample was pretty big and that might affect, anyway, so I found this in one of the review books. So let me just clean up what I said yesterday a little bit on this. This is nothing unique to t-distribution necessarily, but this is it. You got a big sample size, right? More than 40. We don't have to say anything about the population distribution, right? Okay. By the central limit theorem, we know the sampling distribution is normal. But this is what I was alluding to yesterday. If you've got a fairly decent sample size, remember the population distribution doesn't have to be perfectly normal. This big sample size, all those X bars will get more normal. Okay? So here's, you have to assume the population distribution is normal-ish. Don't ever write down normal-ish on your paper. That's not even a word. But you know what I'm saying here, right? It doesn't have, the population distribution doesn't have to be perfectly normal for the sampling distribution to normalize because of our reasonable sample size. Now, what you do need to be aware of, when you're analyzing your sample, you still don't want any outliers. But if you've got a little bit of skewedness, don't freak out. Okay, that's okay. If the population distribution has a little bit of skewedness, that's going to be all right. The sampling distribution is going to be normal. Now, if you have a small sample size, like we've got here, okay, well, we do need to have the population distribution be very close to normal. Okay, so we still don't want any outliers, and we don't want skewedness. Now, a little bit of skewedness, okay, but if you have a pretty skewed box plot, that would be cause for concern. Okay, so that just cleans up assumption 3 a little bit. When we have a t-distribution, especially, those are kind of the rules we're going to follow. All right, we are going to add a fourth assumption. Okay, we're going to tell our reader, hey, we're doing a t-distribution. So are we supposed to do a t-distribution? Here you'd say yes, because population standard deviation is unknown. Okay, so that is. So I guess, I mean, don't worry about this for tomorrow, but I guess we'd actually, for a z-distribution, we'd put z-distribution here and say yes, because standard deviation is no. I'm not going to grade you down tomorrow if you don't do that, but I guess there would be a fourth assumption. We'd include that now that we have two options. Yeah?
Wait, so for the fourth assumption and check, you put yes because the standard deviation
Is unknown. We have to use the t-distribution because we don't know the population standard deviation. All right, what's next? Test statistic? Did anything change here? You bet. We got a whole different formula to use. In fact, we have two formulas. Okay, the first formula for the confidence interval, it's x bar plus or minus t crit times sample standard deviation over the square root of n. And we also have another formula. We have to figure out what our sample size is to see how much confidence we're going to have in this estimate. So you put degrees of freedom is equal to n minus 1. Those are the two formulas that we're going to use. All right, let's go to calculations. Do we draw a picture when we do a confidence interval? No, we're not going to worry about a picture. Let's plug in the numbers. So let's take care of degrees of freedom first, I guess. Degrees of freedom is equal to 6 minus 1, or 5. And now let's plug in the numbers. Did anybody plug those in yet? You got an x bar and a sample standard deviation for me? Okay, so the x bar is 0.51, and we're looking at S now. Remember, you've got those two different standard deviations when you plug your numbers into the calculator? This is a sample. This wasn't the entire population. So S, the sample standard deviation, is the one we're going to use, and we got 0.0632. Okay, so x bar is 0.51 plus or minus t crit. Back in the old days, when we had the population standard deviation, we know this is 1.645. But remember, the t-distribution is more variable. We're going to have to go further out than 1.645 to capture 90% of these x bars. Okay? Go to your green sheets. You've actually seen this before. You had a problem using this thing. I said we'd talk about it later. I believe it's page 16 on the bottom of your green sheets. It says the t-distribution chart. All right, this chart has to cover every situation for every kind of different sample size. So there's a lot of information on this chart. So they designed it completely different, just to confuse you, I guess. Okay, remember your old chart, your z-scores? Wasn't the z-scores around the outside and the probabilities were on the inside? This is totally backwards. The probabilities are along the top and the t-scores are on the inside. So you're going to be looking at this very different. So let's take a look at the picture on top. That's kind of like our old p-value, right? That's what they're shading for you. Those are the numbers that correspond to the top. Okay, so that shaded part are these numbers along the top. Okay, now let's think about this. If we're doing a 90% confidence interval, this is something you should know for tomorrow. If you're doing a 90% confidence interval, what percent would be over here in this tail? 5%. So look along the top for 5%, 0.05, and then they cheat for you. Go all the way down. They say 90% confidence interval, but you knew that anyway. Now, so that last one, look at this. They're saying, if you take a huge sample, say infinite, that's how big your sample is. Are you feeling pretty good about your prediction for the population standard deviation? You bet. So look at the t-score you would get in that situation. There's our old 1.645. We're so sure we got a really good estimate for the population standard deviation. The t-distribution is exactly going to be the z-distribution. Okay? But what sort of a t-score are we going to have to use for this problem? Because we are not very sure of that population standard deviation. So we have a degrees of freedom of 5. That's what you find along the left-hand side. So along the left-hand side, we're looking for 5 degrees of freedom, and we go over to that 5%, which is the 90% confidence interval, and what number do we see? 2.015. Hey, we got to go more than 1.645 standard deviations. Why? I don't trust you very much. These X-bars are going to be way more spread out due to that uncertainty. Okay, so that's the guy we're plugging in here. 1.5. The sample standard deviation, you got this. And then here now, just be careful, this is just 6, right? Square root of 6. A lot of you want to put the degrees of freedom in there. No, degrees of freedom don't fit in there. It's still divided by the sample size. Okay, you'll do that calculation. Do you think anything's going to change in our conclusion? Will anything change in our conclusion? Yes, no? What do you think? Is anything going to be different in our two-sentence conclusion because we use a t-distribution? No, it stays the same. So those are the major differences. All right, let's do a hypothesis test. Let's see what would be different about a hypothesis test. What's the first thing we do in a hypothesis test? Population parameter, is that going to change? No. These are our assumptions, is that going to change? We do have a null and alternate hypothesis. Let me make something up. It's not going to change, but I'll just do it for the purposes of this problem. Mu is 0.46, and we'll say the alternate is not equal to 0.46. Okay, alpha level, whatever that is, that won't change. Test statistic, is that going to be different? We're using a different formula than we did before. You bet. All right, let's go through that formula. All right, we're finding the t-score here. Okay, so the t-score is x bar minus the mean, sample standard deviation over the square root of n. And we're going to have our degrees of freedom for it. What do you need? Kyle, no, not here.
Not here. Mr. Black, is he here?
Yes.
It's just a reprint.
Thanks. Okay, let's go to our calculations now. Do we draw a picture for hypothesis test? You bet. So we draw a picture. Now this isn't new, but I just want to show you again. So they say the true mean is 0.46. We got 0.51. Okay, that's the p-value. But we said it was two-sided. We go to the other side, that far, 0.41. So that's nothing new. I just want to put it up there just to review. That would be the p-value for this one. All right, let's plug in the numbers. So t is going to be equal to 0.51 minus 0.46 over the sample standard deviation, which is 0.0632 divided by the square root of 6. Don't forget degrees of freedom. Need to be up here too someplace. Down here. No. Yeah, degrees of freedom. Degrees of freedom is equal to 6 minus 1, which is 5. You have to show that work that you have to formula. All right, somebody throw that in your calculator real quick. Tell me what that comes out to. .94. Okay. So we know we put that on our picture. 1.94. This would be negative 1.94. Now our job is to find this p-value. All right, let's go to our charts. All right. Now remember, we got to look at this thing differently than we've done in the past. All right, so we're trying to find that shaded region. All right, so we're still on 5 degrees of freedom. So go to your 5 degrees of freedom line and go find 1.94. Does anybody see it? It's not there. Okay? So we're not going to be able to get an exact percentage for the p-value using this chart. But can we get an interval? Is 1.94 between two different t-scores? So what would be the percentage in the tail? What would be the interval for the percentage in that tail for 1.94? Between what and what?
5.
What would be the p-value? What?
5 and 10%.
Between 5 and 10%. Does everybody see that? That t-score fell in that interval. So what I do know is that this is between 5 and 10%. So what is this going to be? Between 5 and 10%. So what's our overall p-value going to then be? Between 10 and 20. And that's as good as we can do using this chart. Okay, so we know that the p-value, the probability of getting an x-bar that far away either direction, is between 10 and 20%. That's what you'll compare against your alpha level. Alpha level is 5%, that's above. 10%, that's still above. If your alpha level would be 20%, that p-value would be okay. Okay, you're not going to get an alpha level inside that range, I would say. Okay. Conclusion, anything going to change in our 3-sentence conclusion? No, it's all the same. Okay. All right, this is real world. This is how you really go out and do a hypothesis test in a confidence interval when you just go take a sample that's blind, okay, and you can determine or drive a confidence. Any questions or comments? Okay. All right, you've got